Project Management, Module 6, Lecture 1, Developing a Project Schedule. Learning objectives for this lecture are to understand the linkage between the WBS and the project network, to diagram a project network using activity on node methods, and to compute the forward and backward path of a project network. The ring assignment is Larson, Chapter 6. So first, let's try to understand what the project network is. It's basically a tool used for planning, scheduling, and monitoring a project while it's in progress. This network is developed from the information collected from the WBS, and it's simply a graphic flowchart of the project job plan. It provides the basis for scheduling labor and equipment, and enhances communication among the project stakeholders. In addition, the project network provides an estimate of project duration and is the basis for budgeting the cash flow of a project. It identifies which activities are critical and should not be delayed. It highlights which activities to consider for compressing the project duration, and it really helps managers get and stay on task. So this figure shows a segment of the WBS example and how the information is used to develop a project network. So in this particular example, the lowest deliverable is the circuit board. And it shows the organization units, the cost accounts, design, production, test, and software. And it also shows which work packages are associated with which cost accounts. So for example, design has WPD111 specifications and WPD12 documentation. Production has 2 work packages, test systems has 1, and software has 2 work packages. The figure also traces out how work packages are used to develop the network, because here you can see, we've got a kind of now a graphical, we're beginning our graphical description of a network. So here A has the work packages listed, D11 and D12. So each of these work packages are put into these nodes. This is what starts as the AON network that will be developing. So here, continuing on, there's 2 paths you can go: A, B, D, E, K, or A, C, D, F, K, right? And another thing that the manager figures out here is he goes into the work packages and he puts the times for completing each part. So for example, A here takes 2 weeks, B takes 5 weeks, C takes 3 weeks, etc. So this actually begins to develop. Now you can actually once you get these times figured out, you can actually go in and the manager can schedule resources and budgets with actual dates on them. So we'll continue developing this example in slides to follow. So when you do the project network, there's a lot of jargon that gets thrown around, and our book kind of gives a list of this kind of terminology you see. First of all, they define what's called an activity. It's an element of the project that requires time, but it may not require resources. Parallel activities. These are activities that can take place at the same time if so desired. It's what's called burst activities. This is an activity that has more than one activity immediately following it. So it's more than one dependency arrow flowing from it. I'll show you an example of this. It's like one box going multiple ways. It's what's called a merge activity. This is an activity that has more than one activity immediately preceding it, and more than one dependency arrow flowing to it. Path. This is a sequence of connected dependent activities. And finally, what's called a critical path. This is the path of the longest duration through the network. The book also defines what's called the 8 rules that apply when developing a project network. So this is to make sure everybody's on the same page when you look at the project network. Everybody can read it the same way. So networks flow typically from left to right. An activity cannot begin until all preceding connected activities have been completed. Arrows on networks indicate precedent and flow and cannot cross over each other. An activity should have a unique identification number. An activity identification number must be greater than that of any activities that precede it. Looping is not allowed. Conditional statements are not allowed. Where there are multiple starts, a common start node can be used to indicate a clear project beginning on the network. Similarly, a single project end node can be used to indicate a clear ending. So here's an example. This uses what's called the activity on node or AON fundamentals. So this showed basically the building block. So an activity is represented by a block or what's called a node. This node can take many forms, but in recent years, the node has been represented by most people as a rectangle or a box. The dependencies among activities are denoted by arrows between the boxes on the AON network. So for example, here you see A going to B and B going to C. So the way this is stated in words is like A is preceded by nothing. There's nothing that comes before A. B is preceded by A. C is preceded by B. So here's another example where X can go to Y or X can go to Z. So this is what's called a burst activity. You see, one node can go two different ways. As this points out, that Y and Z can begin at the same time if you wish. That there's no limit on when you start these. So here you can see what's called a merge activity. We have J, K, and L going into a single node. A merge activity. And here you can see is a situation where Z is preceded by X and Y, and AA is preceded by X and Y. So here you can see that these arrows can cross over each other. There's nothing wrong with that. You see the case here. They can be bent, or they can be any length or shape. You just have to make sure you get the what precedes and what comes after it correct. These relationships, typically you start with a word description and then you form the graphical flow chart so everybody can read. So you got to keep track of what's called predecessor activities. What activities have to be completed before a certain activity. For example, like B is preceded by A, right? So stuff like that. Which activities must follow in that activity? Which activities can occur while this activity is taking place? These are known as concurrent or parallel ones, like X and Y here. So all these things you get used to, and you'll practice in the case study. So here's some information for simplified projects given in the table below. This project represents a new automated warehouse system for picking frozen food package orders and moving them to a staging area for delivery to stores. So you can see this is kind of like a word description. You can see the activities are listed in a table format. Activity A is defined requirements, and that's preceded by nothing. Activity B is assigned team, that's preceded by A, and so on down the list. So this figure shows, the first attempt of actually constructing the AON project network from the information in the table given. You can see it starts with A, is preceded by nothing, and then it goes to B, and then to C. And then you continue on with B and then C, continuing on down the table. And here you can see also that after A is completed, B and C can take place concurrently if desired. So this figure in our textbook shows the completed network with all the activities. So here I would encourage you to go through the table and verify that that's exactly what this graphical network shows. You can see, that's one advantage of this graphical approach is that this is actually easier to read than following this table format, right? You can sort of, if you're here, you know what has to come before it, and you know what can come after it. So it makes it very easy to figure out, how to get the task done that you need to do. So drawing the project network, that graphical form we saw earlier, places the activities in the right sequence, but we also need to be able to, put times on things. So the activity time estimates these are taken from the work package, and they're actually added to the network. So by performing a few simple computations, adding and subtracting, this allows with the times, this allows the project manager to complete a process which is known as a forward and backward pass, and we'll talk more about that when we look at an example. But basically, completing of the forward and backward pass will answer these following questions. So here, for example, the forward pass is gonna give you the earliest time to completion. So how soon can the activity start? This is the early start, and it's denoted by ES. How soon can the activity finish? That's an early finish. That's what it's known as. That's EF. How soon can the project finish? This is expected time, or TE. So in a lot of these diagrams, you'll see these ES, EF, TE. That you'll see those in the graphical charts. The backward pass gives you the latest time to completion. So how late can the activity start? That's LS. How late can the activity finish? That's LF. Which activities represent the critical path? That's CP, critical path. How long can the activity be delayed? That's what's known as the slack or float. So it's SL. So this last one is kind of important. This slack or float provides flexibility in the project schedule, because if your project has a slack or a float amount of time, project managers can use that to shift activities and resources to meet the project objectives and priorities. So this is quite simply, this is the amount of time an activity can be delayed without impacting other activities or the project end dates and changes over the course of the project implementation. So here, this continue with the automated workhouse example, and let's say we went into the work packages and we got the activity times, and so activity A 10 work days, activity B takes 5 work days. So the first thing we do is we need to get this information from the work packages. Then we'll start with what's called a forward pass and do the earliest times. So the forward pass starts with the first project activities and traces each path, the chain of sequence activities through the network to the last project activities. So as you trace along the path, you add up these activity times. The longest path will denote the project completion time for the plan, and it's what's called the critical path, because that's the path that's going to take the longest through the network. So here we've collected this information, and now we can put that information on our activity on node network. You see A here we put 10 work days. Activity, we put all these down from the previous table. So activity E has 50 days. So we start back here at time 0, and we just kind of march our way forward to figure out exactly what the critical path is. And see here you have this what's called, when you're building these activity on node networks, you kind of make this little tic-tac-toe hashtag kind of design. This has a legend. So for example, the top blocks here, we're going to fill out all this information in each of these blocks. So the duration, these numbers here that are laid out, those come from the work packages. The description, those come from the previous page. And the idea is, here it's this letters A, B, C, D, E, F, G, and H. So as we go through here, we're gonna figure out ES, for each one of these. That's the early start time. We're going to figure out, EF for each of these. That's the early finish time, the slack time, and LS and LF. Each of these are going to be filled out. So when this thing is done, we're going to have numbers in each one of these little blocks that are empty right now. So first of all, we go through and we here the early start time for A, we start at 0. So we fill out these for the upper part here, and then so for the early finish time for A is 10, right? Because it takes 10 days. So 0 plus 10, you got 10 there, right? So now we go to B. So you got 10 here. That carries on from here, and then the 10 plus 5 gets 15 to there, right? So you can see how this sort of works. The 15 here goes here. 15 plus 20, that's 35. The 35 goes here, and you got 35 plus 35 is 70. So on this path, it looks like 70, right? Well, you can follow through exactly the same kind of procedure. The 10 for the middle path. 10 goes here, 10 plus 25 is 35. 35 goes here, 35 plus 50 is 85. So this path has 85. And now down here you can do the same thing. The 35 carries to here. 35 plus 15 is 50. So that's 50 here, right? So here you can actually see how long it takes each of these paths to be done. So if this top from going from here all the way around to here takes 70 days. Starting here, going all the way through takes 85, and then going this path takes 50. We can also see, some of these like activity H here. This activity here, it's a merge activity, right? Because it's preceded by more than one activity, right? It's preceded by G, E, and F that merge into it. So, the key thing when you get all this drawn is you ask, which activity controls this, and the answer is obviously E here controls it, right? Because E takes the longest amount of time, 85 days. So if activity E is delayed, activity H will be delayed, right? So, but if this activity G is delayed a few days, it's not going to matter because this is going to take 85 days, right? So this activity, this path through here could be delayed, 15 days, and it's not going to delay the time of H being done, right? Because then they'll both be 85, right? So this forward path is, is what we've done first here. We've calculated what's known as the forward path. And that really just requires you to remember three things. You just do exactly what we did here. You add up the ES plus the duration, get the EF time, and then and you carry on from block to block. This one becomes over here. This block's EF becomes this block's ES, and then you add the ES plus the duration here to get the EF, just like we did. So that's computing the forward path. So let's talk about what's known as the backward path now. So once we've completed the forward path, the next step to finish the project network is to complete what's known as the backward pass. So before the backward pass can be completed, you have to have a late finish for the last activity has to be determined. Now, typically, you know, in the early planning stages, this is usually set to the early finish time of the last activity. Um, in some cases, you know, an imposed project duration deadline actually exists, and you know, if the boss says, you know, this project has to be completed in not 100 days, but you know, 110 days, well, then you can move. You would put 110 here for the LF for the last project activity. This example, we'll follow the textbook's example, and we'll assume that we can accept the EF project duration equal to 100 work days. So here I've copied over the forward pass, the last block, and so we're gonna take the 100 here and put it down here. Now our goal here is to figure out the duration times are given, but we got to figure out the LS values. And so the way you do that is that you simply subtract the LF value from the duration, and that tells you the LS value. So 100 minus 15 is 85, and so the 85 gets moved here, here, and there for the LF times. Then you can keep going. So here 85 minus 50 is 35. That 35 gets moved to here, and 35 minus 25 is 10, and the 10 gets moved to here, and 10 minus 10 is 0. And here you can so that I did the middle path, and you can go back and you can do the upper path and the lower path and check those times. So what have we done? So having completed the forward and backward path, we now have, if you look at the legend here, we have the ES times and the ELF times, the LF times and the LS times. We have to figure out the slack times. And so in the next lecture, I'll go through how to compute the slack times.